this session. So you'll be done with induction at the end of this session, and you can then focus completely on working on that assignment. All right. We'll be done once we're done with induction by the end of this session. Now, first we'll talk about the idea of divisibility, because we'll be trying to use induction in order to prove the divisibility of some term. All right, that the fact that some term is divisible by some other term. For that, let's just talk about what divisibility, what we mean by divisibility. For any two integers a and b, where a will never be equal to 0, if we say that a divides b, we represent it in this way. All right, in this course, whenever you see something like this, two variables, then partition in between, it means that a divides b. If you see this symbol, partitioning, dividing up two variables, then it means that the variable on the left side divides the variable on the right side. A divides b. All right. So what does it mean to say that a divides b? It means that if you divide b by a, you will get, in the result, you will get another integer. So basically, for some integer c, we can say that b is equal to ac, right? So basically, b can be represented as the multiplication of the factors a and c. Okay. So that's what it means to say that a divides b, or b is divisible by a. Okay, that's how we say it. So this is the specific representation we use to express that some term is divisible by some other term. And if we want to say that a given term is not divisible, sorry, if you want to say something like b is not divisible by a, or some term does not divide another term, that is a does not divide b, then what we do is we just cut across that specific partition. All right, you see this partition here, this vertical line, this represents that a divides b. Here, if you see a symbol like this, you should say that, okay, a does not divide b. If you see a symbol like that, that is how we represent this, represent divisibility. Okay, now to prove the idea that some number divides a term, we'll use induction. Okay, so we'll see how induction is used to solve problems of this format. There are other ideas in divisibility as well. We're not going to delve deeper into that. Those ideas will be discussed in number theory. Okay, but for here, the reason we are discussing divisibility just a little bit here is because we are going to use induction to prove that 7 divides this term. Okay, and any problem of this format can be solved, or any statement of this format can be proved using induction. Okay, so 7 divides this term. 7 divides 3 to the power of 2n plus 2 to the power of n plus 2 for all non-negative integers n. So for that, this we are going to try to prove using induction. Now, if it's all non-negative integers, what is the lowest possible value of n? What is the lowest possible value of n if it's all non-negative? 0, exactly. And now in induction, what do we have? Basic step and inductive step. In the basic step, what do we have to prove? A proof by induction consists of 2 steps, right? Basic step and the inductive step. What do we have to prove in the basic step?
Pk is true.
Is that it? Is that the one, though? No. Remember, in the basic step, we prove that the statement holds true for the lowest possible value, whether it's 1, whether it's 0, whether it's 2, whatever it is. In the basic step, remember, the basic step we prove that PB is true, where B is the lowest possible value of n. Okay. So here as well, in the basic step, once again, what will we prove? What is the lowest possible value of n here? You guys have already stated that. What is the lowest possible value of n here? N is non-negative integer. For all non-negative integers n, right? So lowest possible value of n is 0. Yes. So basic step, we have to prove that this statement holds true for what value? 0, right? Basic step, we prove the statement for the least value that we have in the range. Okay, the lowest value is 0. So in the basic step, you have to prove that P0 is true. Our ultimate goal is to prove that Pn is true. And in the basic step, as per the rules of induction, as per the process of proving something by induction, in the basic step, we'll prove that the statement is true for 0. Okay. So basically, if you have n is equal to 0, what do you have here? 3 to the power of 0 plus 1. So 3 to the power of 1. 2 to the power of 0 plus 2. So 2 to the power of 2. So you have 3 to the power of 1 plus 2 to the power of 2 in the right hand side. Okay. What is that? 3 plus 2 squared. 3 plus 4. What is that?
7.
What do we get from here? 7. Exactly. Is 7 divisible by 7? Yes. So basically, 7 does divide the term here. We have here for n is equal to 0. So there you go. Base case proved, as simple as that. That's the basic step. So we see that the statement is true for P0. That is the basic step. In the inductive step, what do we do? In the inductive step, we assume that the statement is true for some integer k, and based on that assumption, we have to prove that the statement is true for some integer k plus 1. That is the next integer. We are allowed to assume that the statement is true for some integer k. We have to prove. What do we have to prove? We have to prove that the statement is true for the next integer, k plus 1. Okay? So yeah. So if based on the assumption, we can say that 7 divides this term, can we not? If pk is true, what does it mean? If pk is true, what does it mean? It means that 7 divides this term. 3 to the power of 2k plus 1 plus 2 to the power of k plus 2. It divides this term, yes. And if 7 divides this term, what does that mean? It means that once 7 divides this term, the result will be some integer, right? Remember here, if A divides B, we can say that there's some integer C such that B is equal to AC. Similarly, based on this assumption, 7 divides 3 to the power of 2k plus 1 plus 2 to the power of k plus 2. Based on this assumption, we can say that there's some integer Q such that 3 to the power of 2k plus 1 plus 2 to the power of k plus 2 is equal to 7q. Yeah?
Yes, miss.
Okay. So now what we'll do is we'll use this to get a value for 3 to the power of 2k plus 1. That is 2 to the power of k plus 2. If we take it to the right hand side, we get 3 to the power of 2k plus 1 equals to 7q minus 2 to the power of k plus 2, which holds based on the assumption. We are allowed to make this assumption, and based on the assumption, we can say that 3 to the power of 2k plus 1 is equal to 7q minus 2 to the power of k plus 2 for some integer q. Okay. Now, the reason we are doing this is, first, think about what do we have to prove. We are allowed to assume that pk is true. Based on this assumption, what do we have to prove? Proof korte hobe ki in the inductive step?
The equation in the bracket is divisible by 7.
Come again? What do we have to prove?
PK plus 1.
What now? What one?
Miss PK plus 1. I'm not sure.
pk plus 1. That's what we have to prove. That's correct. What is pk plus 1? Why are you not sure? We discussed this already, or didn't we? Induction
Miss,
আমরা কি করি?
I'm
Inductive
just
step কি
finding
করি?
it hard. Like this chapter, miss.
Basic step
It's
we
hard
do-
lecture, miss.
Okay, so if the problem is with the concept, then you're going to have to make sure first that you understand the concept of induction, all right? We discussed this in the last session already. You can give that recording a listen. Also, you can schedule a consultation session with me to understand the concept further. If it seems hard, it must be hard because maybe the idea of induction is not clear to you yet. So in induction, what do we do? Basic step ki kori? Basic step we prove that the statement is true for the lowest possible value of n, which is 0. We did that. All right? Lowest possible value of n is 0. We did that. Inductive step ki kori? Inductive step amra, based on the assumption that the statement is true for some integer k, any integer k, we have to prove that the statement must be true for k plus 1. একটা implication proof করতে হবে, implication that pk implies pk plus 1. এই implicationটা proof করতে হবে, pk implies pk plus 1. That is statement k এর জন্য true হলে k plus 1 এর জন্য true হবে. So we are allowed to assume that pk is true. Assumption key, assumption is that pk is true, and based on that assumption we have to prove that pk plus 1 is also true. Okay, and now assumption যেটা যে pk is true, ওটার basis আমরা কি বলতে পারি? 7 divides this term where n is equal to k. And based on this assumption, what do we have to prove? We have to prove that 7 divides what term? 7 divides what? n এর value এখন কি হবে? The part that we have to prove, pk plus 1. We have to prove that pk plus 1 is true. In order to be able to prove that, pk plus 1 is true, what do we have to show? We have to show that 7 divides 3 to the power of 2 into k plus 1 plus 1. That is 2k plus 2 plus 1. And here, k plus 1 plus 2, that is k plus 3. All right. So basically, to prove pk plus 1, we have to show that 7 divides 3 to the power of 2k plus 3 plus 2 to the power of k plus 3. Right?
Yes, miss.
Does it make sense, guys?
Yes, ma'am.
So for pk plus 1, n will be replaced by what? N will be replaced by k plus 1. Okay. And then the term you get, you have to prove that that term is divisible by 7 based on this assumption. Now, a assumption basis, we can also say that since 7 divides this term, dharo, if some variable a, some term a, which will never be equal to 0, if some term a divides b, what does it mean? It means that in the result you will get some integer, all right? And you can say that b is equal to ac basically. For some integer c, you can say that b is equal to ac. Only then you can say that a divides b, right? B is equal to ac, and because of that a divides b, right? So we can say something like this. If a divides b, then b is equal to ac for some integer c. Okay. So similarly,
Yes.
since 7 divides this number, we can say that for some integer q, this term is equivalent to 7q. 7 multiplied with that integer q. All right. So from that, we can also say that 3 to the power of 2k plus 1 is equal to 7k minus 2 to the power of k plus 2. Now, what is the purpose of doing this? Understand that. That is the more important thing. Why are we doing this? Because আমাদেরকে ultimately prove করতে হবে যে এই যে এখানে n এর জায়গায় k plus 1 বসালে, n এর জায়গায় k plus 1 বসালে এই দুই জায়গায়, the term that we get, it is divisible by 7. That's what we have to prove. Okay? It's divisible by 7. So, how we will prove this is by somehow converting this term into a certain format where you have 7 in common. Okay, see here, b is divisible by a because b is equal to ac. ঠিক আছে, because এখানে a আছে. Because if you represent b as this, if you can represent b as the multiplication of these two factors, then it means that b can be divided by a because a is here, right? Similarly, we'll try to somehow represent that term where 7 is a factor. Represent 7 as a factor in that term. And to convert to that, it'll be just easier if we have common terms in the term on the right hand side, the term that has to be divided. Yeah. And in order to do that, we do something like this. You'll just see now. All right. So first of all, for pk plus 1, n will be replaced with k plus 1, right? So we get this. N k plus 1, n k plus 1. From there, we get 3 to the power of 2k plus 3 plus 2 to the power of k plus 3. Now see here, 3 to the power of 2k plus 3 can be represented in this way, right? 2k plus 3k, 2k plus 3, 2k plus 3. This term can be represented in this way, right? 2k plus 3 is also 2k plus 1 plus 2. আমি কিভাবে বলতে পারি না যে 2k plus 3 is equal to 2k plus 1 plus 2. I can say that, right? So 3 to the power of 2k plus 1 plus 2. It's the same thing so far. Now, we know that we can distribute, since 3 to the power of this term these are summed. These are some terms in the power. Power এর মধ্যে যেহেতু some term আছে, we know that we can distribute the power among the base, all right? We can distribute the base among the power, all right? So power এর যেহেতু some term আছে, 2k plus 1 plus 2, we can say that this is equivalent to 3 to the power of 2k plus 1 into 3 square. So basically, you can get back to this stage from here. So we can do something like this. Same base. So you can just combine this and get back here. 3 to the power of 2k plus 1 plus 2 and then come back here. So what we will do is we'll break down this term. A term take bhangbo. How will we break it? 2k plus 1 plus 2 and then distribute the base 3 to the power of 2k plus 1 into 3 square. Right? What is the purpose of doing this? Because if you do it, if you break it down in this way, you have 3 to the power of 2k plus 1 here. Right? And we know that 3 to the power of 2k plus 1, based on the assumption, we know that 3 to the power of 2k plus 1 is equal to 7q minus 2 to the power of k plus 2 for some integer q. All right? Based on the assumption. That is the reason we are breaking this term down and we are trying to extract this term from here. Okay? And why are we doing that then? See, if you break it down and we get 3 to the power of 2k plus 1 and we replace 3 to the power of 2k plus 1 with 7q minus 2 to the power of k plus 2, now we have terms here, power terms here with the same basis. Okay? Based with the same high, somehow we can convert it and find common terms there. Okay, that's the reason we are trying to do this. That is the reason 3 to the power of 2k plus 1 ke bhabe represent kora hoyeche, so that later on 3 to the power of 2k plus 1 ke somehow I can replace it with 7q minus 2 to the power of k plus 2 and somehow change the terms with the same base in such a way that there are common terms in that there. Okay, so that's what we will do here. So first of all, replacing 3 to the power of 2k plus 1 with this term, we distribute 9 among this. All right. So we have 9 multiplied by 7q and 9 multiplied with 2 to the power of k plus 2. 9 multiplied with 7q is also equivalent to 7 multiplied with 9q. Right. 9 into 7q is the same thing as 7 into 9q. So instead of doing 9 into 7q, we'll do 7 into 9q, because remember what is our ultimate goal? Our ultimate goal is to somehow find common 7s here in the sum terms and take the 7 in common. So we can say that 7 is here in this term as a factor. So this term is divisible by 7. Okay. So 9 into 7q can we just represent korchi in a different way. 7 into 9q. And here we have 9 into 2 to the power of k plus 2. All right. So far, so good. All right. Now 2 to the power of k plus 3. A 2 to the power of k plus 3, this term, similarly, just like before, can we not say that it's equivalent to 2 to the power of k plus 2 plus 1? Basically, k plus 3 power taki, we are breaking it down, k plus 2 plus 1. Right. And then, since a base the powers are in this sum term, we can distribute the base. That is, we can say that this is equivalent to 2 to the power of k plus 2 multiplied with 2 to the power of 1. Okay, we can say that. So we have 2 multiplied with 2 to the power of k plus 2. Now see 2 to the power of k plus 3, 2 to the power of k plus 3 here, 2 to the power of k plus 3 is transformed into 2 to the power of k plus 2 into 2. Okay. So we have 2 into 2 to the power of k plus 2 here and 9 into 2 to the power of k plus 2 here. So if you take 2 to the power of k plus 2 in common here, what do you get? Minus 9 plus 2 or 2 minus 7. Sorry, 2 minus 9. Minus 9 plus 2 or 2 minus 9. That will give us what? Guys?
Minus 7.
7, miss.
Minus 7. Exactly. So you see, finally, we have this situation where both sum terms have the term 7 in common. So if you take that in common, what do you get? 7 into 9q minus 2 to the power of k plus 2. Here, we know that q is an integer. So 9q will obviously be an integer. We know that k is an integer. 2 to the power of k plus 2 will also be an integer. The difference between two integers will also be an integer. 7 multiplied with some integer, that is the term we get from this term where n is equal to k plus 1. Now, tell me, is this term divisible by 7? What do you think?
Yes, miss.
Obviously, this term is divisible by 7. এখানে আছে একটা integer আর এখানে আছে 7. 7 is a factor here. So obviously, this term is divisible by 7. Okay. So since this term is divisible by 7, what have we done just now? We have proved that this statement is true for k plus 1. Based on the rules of induction, we proved in the basic step that it's true for 0, the base case. And then we, assuming that it's true for k, we proved that this statement is true for k plus 1. Hence, since we have proved all of that, combining the basic step and the inductive step together, we can say that Pn is true for all integers n. Okay, Pn is true for all non-negative integers, not all integers. Pn is true for all non-negative integers n. Okay, based on the rules of induction. There you go. So whenever you're asked to prove something related to divisibility, using induction. Let's say divisibility proof korte bola holo and you use induction for that. So remember this, remember what we've done here. Okay, so just trying somehow to convert the k plus 1th term here for n is equal to k plus 1, j term ta paba, trying somehow to manipulate that term so that you get a factor there which is the same as the divisor. এখানে 7 is the divisor. এই যে এই টার্মটাতে যদি আমি 7 কে ফ্যাক্টর হিসেবে আনতে পারি, I can right away say that this term is divisible by 7 or any multiple of 7 for that matter. For example, এখানে 7 এর জায়গায় যদি 14 থাকতো, we could still say that this term is divisible by 7. Yeah, so just remember the process here, how we did it, how we what's the process of doing this. Okay, first, based on the assumption, this is something that we are allowed to assume that it's true. Okay, based on that assumption, we have to prove that it's true for k plus 1. From there, we converted to, we found a term for 3 to the power of 2k plus 1 so that we have common terms here. Okay, and from the common terms, we got to a point where we have 7 there as a factor, and that tells us that this term is divisible by 7. Yeah, so just remember the process more importantly. Okay, so any questions?
Miss, can you go to the previous slide?
Yes,
The
sure.
divisibility slide, Miss. The before one.
Yeah.
Miss, here, like, provided that there exists an integer c such that b equals to ac. Miss, এটা মানে একটু বুঝতে confused.
ধরো আমরা যদি বলি যে an integer divides another integer, ঠিক আছে, 3 divides 6, why can we say that? That is, 6 can be divided by 3. Why can we say that? Because if you divide 6 by 3, you get 2 in the result. Or 6 can be represented how? 3 multiplied by 2. Okay, for some integer, which in this case is 2, you have 3 multiplied by 2. 6 can be represented in that way. All right, so b, if you can represent b as the product of 2 integers where one of them is the divisor itself and the other one is some integer, only then you can say that a divides b. Yes, here 3 divides 6. এই জিনিসটা তুমি আমরা তো জানি যে 6 is divisible by 3, right? We know that 6 is divisible by 3, but why? Because if you divide 6 by 3, you get an integer as a result. Or in other words, 6 can be represented as the product of 3 and 2. Since 3 is there in the product, it's obviously divisible by 3. And also the other one is an integer. Why is 5 not divisible by 2? Because 5 কে তুমি ওইভাবে represent করতে পারবা না. Can you represent 5 in that way, a product of 2 integers where one of them is 2? Can you? No. So that's why 5 is not divisible by 2. 2 divides 5 means that the one on the right hand side, 5, must be, it must be possible to represent 5 in this way, in this format. All right, product of 2 integers where one is 2 and the other one is some other integer. Okay, it's not possible. Or in other words, if you divide 5 by 2, the result will not be an integer. The result will be a fraction. All right, it will not be a whole number, basically. So yeah, that is what it means. That if you divide, if we say that a divides b, if we say something like a divides b, it means that b is equal to ac for some integer c. Now is that clear?
Yes, Miss.
Okay, any other questions regarding the proof though? All right then. So I'm assuming that you guys all understood it. You guys can take a look at it later on in your free time, and then yeah, if you still have any confusion, you can get back to me later on. All right. However, please make sure that you understand this, because in the exam you might be given, let's say, some random problem regarding divisibility and asked to prove a statement regarding divisibility using induction. Okay, so you have to understand the process of how we proved it using induction. So if you have any questions now or later, just let me know. Okay, now we'll look at the process of strong induction. Okay, what is strong induction? Strong induction is just a bit of development on induction. Yeah, sorry.
Miss, I
Is there a
said it's
question?
more difficult than normal induction.
Oh, okay. No, it actually makes our life easier, because in strong induction, we have a stronger assumption. So in induction, remember, in induction, the basic step, you prove that the statement is true for just one value. Which one specifically? The lowest value of n. You prove the statement for the lowest value of n. All right. And in the inductive step, you have to prove that if pk is true, then pk plus 1 is also true. Here, our assumption is what? Our assumption is pk is true. This is our assumption. This is what we are allowed to assume. And based on that assumption, we have to prove this one. This is the one that we have to prove. Okay. In strong induction, in the basic step, what we do is we prove it instead of proving it just for the lowest value, we prove it for the lowest couple of values. That is, for a range of values, we do the basic step. Okay. And in the inductive step, this is where it makes things easier for us. In the inductive step, we are allowed to assume that the statement is true for a range of values. Okay. That the statement is true for a range of values. Let's say so basically in strong induction, in the base step, how does the basic step change? In the basic step, you prove that P is true not only for the base case, not only for the lowest value, you prove it for a range of values. All right. You prove it for a range of values. B1, then let's say P, B2, let's say P, B3, and so on as per the requirement of your proof. All right. And so on until some point, right? Until some point, let's say Bx, as per the requirement of your proof. Proof করার জন্য যতগুলো base case proof করতে হবে, যতগুলো base case দেখাতে হবে, we'll do that. All right. Why are we doing this? Why are we in the base case, in the basic step? Why are we proving this for multiple values? Because in the inductive step, we are changing the assumption. All right. We are increasing the scope of the assumption. Now the assumption changes. Let's say so far, we assume that the statement is true for k, and hence we have to prove that the statement is true for k plus 1. In the assumption, we assume that the statement is true for a range of values, all right, starting from the lowest possible value until k. Let's say the assumption is, in the assumption, we are allowed to assume something like this, that the statement is true for a range of values. But we have to prove what? Prove that based on this assumption that the statement is true, this time for a range of values, the statement is true, we have to prove that the statement holds for k plus 1. That is the next integer. Okay. The statement holds for the next integer. Previously, in induction, we proved that the statement is true for some integer k, and based on that assumption, we proved that the statement is true for the next integer k plus 1. Here, in strong induction, what changes in the assumption is that instead of assuming it just one given integer, একটা specific integer k, এটার জন্য assume করার জায়গায় we'll assume it for a range of values. Okay, we'll assume it for a range of values and prove which one? Prove that the statement is true for the next value. So the assumption is a bit stronger. Okay, the assumption, by stronger I mean that the assumption covers a bigger scope, so it makes our life a lot easier. Okay, and why can we do this? Why is it that we are able to do this? Because in the base step, we are proving it for a range of values as well. Okay. So what will be Bx? That is what will, for how many values you'd have to prove the basic step. It depends on the problem depends on the statement that you're trying to prove. It depends on the specific problem that you're trying to tackle. All right. On that, it will depend. Like basic step, আমাদের কয়টা ভ্যালুর জন্য proof করতে হবে. Okay. And based on that, we'll move on to the inductive step where we assume for a range of values, and then from that, we have to prove that the statement is true for, let's say, k plus 1. What is the point of k plus 1? Proving that the statement is true for the next integer. Let's say, for example, if we said that the range here, the assumption, we are allowed to assume that the statement is true for some value b1, that is the least value, the lowest value b1 until before k. If we say something like that, sorry, until before k. For all values before k, the statement is true. If that is our assumption, in that case, what do we have to prove? Guys, okay. Think about the point of k plus 1. What is the point of k plus 1 at all? The k plus 1 কিসের জন্য? Why k plus 1? In the inductive step, we are allowed to assume that the statement is true for pk. We have to prove that the statement is also true for the next integer. What is the next integer? K এর পরের integer কি?
K plus 1.
Exactly, k plus 1. All right. So in the inductive step, always assumption এ যেটা থাকবে ওটার বেসিসে তোমার প্রুফ করতে হবে for the next integer. তুমি ধরো for example এখানে যদি if you assume that the statement in the assumption as a inductive step এর assumption এ তুমি বললা যে I am assuming that the statement is true for pk minus 1. In that case তোমাকে প্রুফ করতে হবে কোনটা?
PK.
pk, exactly. So the point of k plus 1, এখানে k plus 1 আছে to represent what? To represent the idea of the next integer. That is, pk is true, it's also true for the next integer. To represent the idea of the next integer, we're using k plus 1 here. So similarly, in strong induction, let's say, if we said that the statement in the assumption, if we assume that the statement is true for a range of values until before k, instead of until k, if we say until before k, right? In that case, what do we have to prove? We have to prove it for the next integer, which is k. All right? If
This
the
K
assumption is k minus 1 can have until before k, right? So k minus 1 is less than k. For all values starting from b1 until before k. All right? For all values from b1, from all values that are less than k, we are assuming that the statement is true. For all values that are less than k, we are assuming that the statement is true. If that is our assumption, we have to prove it for the next integer. K, all values less than k, for those values, if it's true, if that's our assumption, we have to prove what? For the next integer. Which one is the next integer? Next integer konta? Is it k
Oh,
minus
now
1?
it's
No,
K.
it's k. K. Yeah. So that's what I'm saying. Just don't get stuck up on the idea of k plus 1. K plus 1 is there just to represent the next integer. তোমার প্রবলেম অনুযায়ী তোমার যদি ইজি হয় যে আমি মানে instead of like if I do something like this, if I say that strong induction, I'm talking about strong induction. In the strong induction, if we say that we assume that the statement is true for a range of values, in that case a range of values which covers b1 until k পর্যন্ত, until k, if we say that, then we have to prove for the next integer, which is k plus 1. If we say that in the assumption the statement is true for all values that are less than k, in that case we have to prove that the statement is true for k. Whichever is easier for your problem, do that. Okay, don't get stuck up in k plus 1. You can also prove in that way, obviously, but you'll see in the next couple of proof that instead of trying to prove for k plus 1, what we will do is in the assumption we'll assume that the statement is true for a range of values until before k, that is all values less than k. All values less than k, for those the statement is true, and we'll try to prove that the statement is true for the next value, which is k. We'll do that because that makes our problem neater or tidier. Etar jaygaye jodi if you did something like this, it did not work, it would still work. But just to make the solution a bit neater, we'll do something like this. All right? Ultimately, k plus 1 is there for the idea of the next integer. Ekhaneo to we still have the next integer. If you're saying the assumption covers all values that are less than k up until before k, basically, that is k minus 1 পর্যন্ত যদি থাকে, that is, if you say something like this, that b1 until k minus 1, in that case, what is the thing that we have to prove? That the statement is true for k. All right? Just keep that in mind. Now, once again, strong induction. In the basic step, we prove it for a range of values. In the inductive step, the assumption is a bit covers a bigger scope. That is, in the assumption, we are allowed to assume that the statement is true for a range of values. And based on this assumption, we have to prove that the statement must be true for the next value as well. Okay? So yeah, let's try to solve something using strong induction. We are asked to prove that this expression represents the Fibonacci sequence. Okay, what is the Fibonacci sequence? These are some of the first few terms of the Fibonacci sequence. One definition of one way of defining the Fibonacci sequence, the one that is common to most of us, I believe, is this one, this recursive definition. If this is the Fibonacci sequence, then this sequence can be defined in this way, a recursive definition, where you have a base case gulo ki, base case hoche ki f0, that is the value in the 0th index is 0, the value in the 1th index is 1. So these are the two base cases, and based on these base cases, we can derive the rest of the sequence. So f3 will be what? Based on this equation, f3 will be summation of the previous two values. See, fn, this equation represents the rest of the sequence, right? That is, any number in a certain position in the sequence can be found from the summation of the preceding two numbers, right? So if you already have f0 and f1, what will be f2? Guys, what will be f2 here? N is equal to 2, you know, what do we get here? For n is equal to 2, here what do we get?
0 plus 1.
Yes, 0 plus 1. Because for n is equal to 2, here we get f1 and here we get f0. We know that f1 and f0 are 1 and 0. 1 plus 0 gives us 1. And as you can see, here for n is equal to 2, we have 1 here. For n is equal to 3, we have 2 here, and so on. Okay? So that is the Fibonacci sequence. And one way of defining this Fibonacci sequence is this recursive definition, which most of us should be familiar with. All right? So f0, f1 being the base case. See, f0, f1, the first two, those are fixed. Those are the base cases and those are fixed. And after that, everything else will be derived based on this, based on the base case and this definition. So the second one, as you've seen, gives us 0 plus 1, 1. The index 2 value, the value in index 2. The value in index 3, what do we get for that? We have to sum up the previous two values, 1 and 1. 1 plus 1, we get 2 here. As you can see, it matches. 2 plus 1, 3. If you place that in this formula, it adds up, all right? Ties up. So yeah, that is the recursive definition. But here, in this problem, we are not going to prove the recursive definition. We know that the recursive definition is true. The recursive definition is used to define the Fibonacci sequence, yeah? So we know that the recursive definition is true. That given that we have these two base cases, the rest of the numbers in the entire sequence can be derived from this equation, okay? We know that that is true. What we have to prove, though, is that this statement also represents every single number in this sequence as per the index value. That is, as per the value of n. That is, for every non-negative integer n, we can use this equation or this expression to derive the value in some position in the Fibonacci sequence, okay? And for this one, you'll notice that we don't need the base cases, okay? This is the equation that we can use, assuming that we don't know the base cases. f0, f1 jodi na jana thake, this equation can be used to derive f0 and f1 as well. See, this statement is not recursive. This is the recursive definition, where you use some previous values to define the next value, and you assume the rest of them to take care of themselves on its own. All right, that's the recursive definition. Here, you see, based on the value of n, you will find the value on that specific index n. All right, you're not relying on the previous values or something like that. So this definition of the Fibonacci sequence, which doesn't rely on the base cases, or which is not recursive basically, which doesn't rely on the previous values, we'll try to prove that this is also valid to define the Fibonacci sequence. In order to do that, what we'll do is, first we'll prove the base cases, and then using the recursive definition, which we know is true, using the recursive definition, if we can somehow show that we can get to this term, recursive definition use kore amra jodi ei term porjonto ashte pari, tar mane that from the recursive definition you can get here. What does it mean? If the recursive definition is true, then this one must be true. Jodi recursive definition theke ekhane ashte paro, that means recursive definition, so we know that it's true. Then if you get here from the recursive definition, then this must be true as well. That is what we are going to try to do. All right? All right, now, so strong induction. Strong induction, and remember again that in the base case, we prove it for more than just the lowest value. Before that, what is the lowest value of n here? We have to prove this statement for we have to prove this statement for every non-negative integer n, right? So what is the lowest value of n?
0.
Yes, that's correct. So for ordinary induction, you'd have to prove it only for 0. In strong induction, you'd have to prove it for more than 0. You'd have to prove it for 0 and 1. Okay, both of them. That is both these base cases. A base case gula amaderke proof korte hobe. Why? Remember again what I said, that recursive definition ta kintu we know that it's true. So we are going to use the recursive definition of the Fibonacci sequence to get here. Ekhon recursive definition use korte hole, recursive definition e ki age duta value use kore to recursive definition exists, right? So if you want to use the recursive definition somewhere down the line in your inductive step, maybe you have to prove that this statement gives the correct value when n is equal to 0 and n is equal to 1. If you want to use the recursive definition somewhere down the line, right? So we want to prove that this this expression can give us any value in the Fibonacci sequence if we know the index. And we will use the recursive definition for that. And in order to use that, we have to show that 0 or 1, এই দুটো ভ্যালু কোত্থেকে আসতেছে? এই দুটো ভ্যালু যে আমরা n equals to 0 or 1 respectively এগুলোর জন্য হচ্ছে কি আমরা এখান থেকে ওই ভ্যালুগুলো পেতে পারি। All right. So for n is equal to 0, what do we get here? 1 plus square root of 5 by 2 to the power of 0. What do we get here for n is equal to 0?
1 by root 5.
Sorry?
1 by root 5.
That is, this one becomes 1. Exactly, 1 by square root of 5. This one to the power of 0 gives us 1. So we have 1 by square root of 5. Here as well, similarly, we'll get 1 by square root of 5. 1 by square root of 5 minus 1 by square root of 5. What do we get in the result?
0.
0.
0. So you see, that's done. So the base case is already proved, right? So that the statement is true for 0. Okay. Now, for n is equal to 1. For n is equal to 1, we have 1 here, 1 here. You will see that ultimately after calculation, you get 1 after that, right? You'll see that. So here, what do we get? 1 by square root of 5 multiplied with 1 plus square root of 5 by 2. N is equal to 1 and 2. That is what we get on in this sum term, right? 1 by square root of 5 multiplied with 1 plus square root of 5 by 2. As simple as that. And here we get 1 by square root of 5 multiplied with 1 minus square root of 5 by 2. The difference between the two. So let's see. 1 by square root of 5 multiplied with 1 plus square root of 5 by 2. As we just discussed, and the rest of it as well. For n is equal to 1. For n is equal to 1. Now, if we take 1 by square root of 5 in common, a1 by square root of 5 যদি আমি এখন common নিই, if we take it in common, what do we get? 1 plus square root of 5 by 2 minus 1 minus square root of 5 by 2. Okay? Denominator same. 1 by square root of 5 common নেওয়ার পরে denominator is same, 2. So we can say that since the denominator is the same, in the numerator we will have 1 plus square root of 5 minus 1, then minus plus square root of 5. We'll get that in the numerator. And then 1 gets cancelled out. What do we get here? 2 square root of 5. If 1 gets cancelled out, 1 minus 1 gets cancelled out, 2 square root of 5 divided by what? 2. 2 square root of 5 divided by 2. So what do we get from there? We get square root of 5. So ekhane 1 by square root of 5 chilo, remember? Multiplied with what? Now square root of 5. So square root of 5 in the denominator, square root of 5 in the numerator. Those two gets cancelled out. And what do we get in the result? 1. So you see, for n is equal to 1 as well, the result is 1. So it can easily be shown that for n is equal to 0 and 1, in the basic step, basically, in the basic step, that is, you can show that for n is equal to 0 and 1, this statement gives us the expected values. Expected hoche giye 0 and 1 respectively. We get those from this statement, from this expression. So the base step, with the basic step is done. Okay. Then in the inductive step, this time, we will first assume that the statement is true for a range of values and then prove that if that is the case, then the statement must be true for the next value. Before we get to that, what we'll do is we'll represent these constants, 1 plus square root of 5 by 2 and 1 minus square root of 5 by 2, these constants using some specific name, all right? Some specific variable name. It's not a variable, it's a constant. It's not a variable, it's a constant. But here, see, we will use alpha and beta to represent the constants 1 plus square root of 5 by 2 and 1 minus square root of 5 by 2 respectively, all right? We'll use alpha and beta to represent these things. 1 plus square root of 5 by 2 will be represented using alpha. 1 minus square root of 5 by 2 will be represented using beta. Why are we doing this? Just to make the whole expression neater. It makes things easier. You'll just see that. All right. So alpha represents the constant 1 plus square root of 5 by 2. Beta represents the constant 1 minus square root of 5 by 2. Now, also, alpha square is equal to alpha plus 1. You'll see that if you try to square 1 plus square root of 5 by 2, if you try to square 1 plus square root of alpha square maniki 1 plus square root of 5 by 2 whole square, right? If you try to do that, you'll see that you'll ultimately get alpha plus 1 in the result. Okay. So that is 1 plus square root of 5 by 2 whole square korle, you'll get 1 plus square root of 5 plus 1 in the result. Okay. So see, 1 plus square root of 5 by 2 whole square. What do we get there? 1 plus square root of 5 by 2 whole square. Okay. So for that, we get what? In the denominator, 2 squared gives us 4. And then in the numerator, we have 1 plus square root of 5 whole square. So a plus b whole square, basically. So a plus b whole square theke, you get 1 plus 2 square root of 5 get 1 plus 2 square root of 5 plus what? Square root of 5 square, right? Square root of 5 whole square will give us what? 5. This is what we get in the numerator. 1 plus square root of 5 whole square, all right? So basically 6 plus 2 square root of 5. That's what we get, all right? That's what we get. Ekhan theke, if you take 2 in common, if you take 2 outside, what do you get? 3 and here plus square root of 5 if you take 2 in common. And then 2 here in the numerator, 2 here in the denominator, what do you get? This turns into 2. 2 and 4, they cancel each other, and then you get 2 in the denominator, okay? And notice that this 3, now we can represent it in this way, 2 plus 1 plus square root of 5. Why are we doing that? See, if we now distribute the denominator among these terms, এই termগুলোর মধ্যে যদি আমি denominatorটাকে distribute করি, then what do we have? 2 by 2, then plus 1 plus square root of 5 divided by 2, right? What is 2 by 2? 2 by 2 is 1. And what is 1 plus square root of 5 by 2? The constant that we originally started with, all right? So you see 1 plus square root of 5 by 2 whole square gives us 1 plus square root of 5 by 2. So basically, alpha, this is alpha, right? This is alpha. Alpha square gives us 1 plus alpha, okay? Yeah. So similarly, if you try it out for beta as well, that is, if you try it out for 1 minus square root of 5 by 2, you'll see that 1 minus square root of 5 by 2 whole square gives you 1 plus 1 minus square root of 5 by 2. So basically, beta square is equal to beta plus 1. So we're representing these two constants with alpha and beta respectively. And we've also seen that alpha square is equal to alpha plus 1, beta square is equal to beta plus 1. There's a purpose of doing these things. You'll see later on, all right? But alpha and beta, we're doing that just to make this solution seem a little less intimidating, okay? So if we represent, and we can do that. These are constants, right? Constants ke ami alpha beta diye represent korte pari, as long as we are not changing the definition of alpha and beta, okay? So Fn now becomes 1 by square root of 5 alpha to the power of n minus 1 by square root of 5 beta to the power of n. So this is how we are going to represent Pn. So far, is there any confusion or question? Guys?
No, miss.
No, miss.
Okay. All right. So we use alpha and beta for those constants, and this is what the equation turns into. This is the equation that we had. This becomes alpha, this becomes beta. So we have now 1 by square root of 5 into alpha to the power of n minus 1 by square root of 5 into beta to the power of n. We've already proved that the statement is true for 0 and 1. It can be easily checked that the statement is true for 0 and 1, right? Now, in the inductive step, again, just like before, we'll assume that the statement, just like we've discussed strong induction, we'll assume that the statement is true for a range of values. Let's say the statement is true for all the values starting from 0 until before k, where k is some integer greater than or equal to 2. K will be some integer greater than or equal to 2. Why k must be greater than or equal to 2? Remember, we are using the recursive definition. We are going to utilize the recursive definition. If k is less than 2, in that case, oje, For example, fn is equal to fn minus 1 plus fn minus 2. Assuming that in this equation, a expression tate n, this n will never be less than 2, assuming that, okay? So we are going to use this recursive definition. So hence, in the assumption, we assume that the statement is true for all values starting from 0 until before k. The entire range of values starting from 0 until before k, we assume that the statement is true. And then we prove that the statement must be true for k as well. We have to prove that the statement is true for k based on this assumption. If this is our assumption, দেখো range টা cover করছে কি 0 less than equal to j less than k, that is until before k. So next integer কোনটা? Next integer to k itself. So you have to prove that the statement is true for k based on this assumption, where k is some integer greater than or equal to 2. Okay. So now, in order to prove that the statement is true for k, we can use the assumption. All right, we can use the hypothesis to prove that. And based on the hypothesis, what can we say about k minus 2 and k minus 1? K minus 2, k minus 1, is it within this range? Assumption ta j range er jonno ache. We're assuming that the statement is true for this range, right? We are assuming that the statement is true for this range. Is k minus 2 and k minus 1 within this range, guys?
Yes.
K minus 2, k minus 1. It's in this range, right? K minus 2 or k minus 1, so these are less than k. So k minus 2 and k minus 1 will be covered within this range. And remember, the assumption is what? The hypothesis is what? That the statement is true for this entire range until before k. And k minus 2 and k minus 1 are less than k. They are in this range. So based on that, we can say that, based on the assumption, we can say that the statement is true for k minus 2. The statement is also true for k minus 1. Okay. Does that make sense, guys? So far, we are only talking about the assumption.
Yes, miss.
Okay. All right. So based on the assumption, we can say that the statement is true for k minus 1 and k minus 2. Since k minus 1 and k minus 2, both of these are less than k. They are within this range. Okay. Now, if pk minus 2 and pk minus 1, if we assume that these two are true, in that case, what does it tell us? pk minus 1, pk minus 2, it is true mane ki? For n is equal to k minus 1 and for n is equal to k minus 2, you can derive the value in the Fibonacci sequence in that specific index using this formula, right? A formula use kore, a formula where n is equal to k minus 1 and n is equal to k minus 2, we can derive that specific value in that index in the Fibonacci sequence. That is what it means, right? When we say that these two are true, this is what it means. It means that fk minus 2 is equal to 1 by square root of 5 alpha to the power of k minus 2 minus 1 by square root of 5 beta to the power of k minus 2. N er jagah k minus 2. That this is true. All right? That this specific value in the Fibonacci sequence in this index, k minus 2 index, can be derived from this equation. That's true. That's our assumption. Similarly, for k minus 1, we are allowed to assume this. Now, what is the purpose of doing this? Remember again, what did I say? We are going to use the recursive definition here. Recursive definition here. Starting from the recursive definition, if we get here, it means that this equation must be true because we know that the recursive definition is correct. The recursive definition holds. We know that. So now we have fk minus 2, which can be represented in this way, fk minus 1, which can be represented in this way based on the assumption. What do we have to show? We have to show that pk is true. That is, fk can be derived from 1 by square root of 5 into alpha to the power of k minus 1 by square root of 5 beta to the power of k. So based on the recursive definition, first of all, what is fk? Recursive definition er basis ei jekhane je recursive definition ta ache eta jodi amra use kori tahle what is fk, guys?
Miss fk minus 1 or plus fk minus 2.
Exactly, correct. So based on the recursive definition, we can say that fk is equal to fk minus 1 plus fk minus 2. That is what the recursive definition tells us, right? Je kono ekta position e, je kono ekta index e, as long as k is greater than or equal to 2, for the value in some index, you can get it by summing up the values in the previous two indexes. All right, that's what the recursive definition tells us. What we will try to do is from here, we will try to get to what? We will try to get to 1 by square root of 5 alpha to the power of k minus 1 by square root of 5 beta to the power of k. That That is what we'll try to do. And if we can do that, এখান থেকে যদি ওখানে যেতে পারি, it means that fk indeed can be represented using that equation, 1 by square root of 5 alpha to the power of k minus 1 by square root of 5 beta to the power of k. Okay, because this is true from here. If we can get here, it means that this is correct as well. This is a correct representation of fk as well. Okay, now let's get to it. Fk minus 1, fk minus 2. So we already know that fk minus 1 and fk minus 2 can be represented this way based on the assumption. Assumption অনুযায়ী আমরা বলতে পারি যে fk minus 1, fk minus 2 can be legitimately represented in this way based on the assumption. Okay, so let's do that. Fk minus 1, fk minus 2 ke replace করলাম with these. Okay, now what we'll do is we'll combine the alpha terms together and the beta terms together. See here, we have alpha and beta here. So আমরা alpha term আর beta term গুলোকে একসাথে করে আনবো so that later on somehow we can combine those terms and get to one alpha term and one beta term. Okay, so এখান থেকে alpha গুলোকে একসাথে করব, beta গুলোকে একসাথে করব. So you have 1 by square root of 5 multiplied with what, alpha to the power of k minus 1 plus alpha to the power of k minus 2, and then here minus. Also remember in the equation we have minus here in between. Okay, the difference is there. Okay, so minus থাকবে এখানে in the middle, minus 1 by square root of 5 commonly you have beta to the power of k minus 1 plus beta to the power of k minus 2. Okay, so that's what we have. Now next what we'll do is we'll try to transform this. How? By keeping a common term. Transforming by keeping a common term for alpha. How do we do that? See, alpha to the power of k minus 1. Yeah, power টা different but base টা same. We can manipulate it. Remember আগের example আমরা কি করেছিলাম? আগের example এ যেসব জায়গায় base same আমরা পাওয়ারটাকে manipulate করে we got to the same term. Now see here, that's what we'll do here as well. Alpha to the power of কি আছে, k minus 1. আমি যদি বলি k minus 1 is equal to k minus 2 plus 1. Am I wrong?
No, ma'am.
K minus 1 is equal to what? K minus 2 plus 1. There's nothing wrong with that, right? So আমি যেটা করব, alpha to the power of k minus 1k, I will represent it as alpha to the power of k minus 2 plus 1. If I do that, k minus 2 plus 1 দিয়ে যদি represent করি, what do I get? K minus 2 plus 1, alpha to the power of k minus 2 plus 1. So power A, there are some terms, k minus 2 and 1, k minus 2 plus 1. So can I not distribute the base in this way? Can I not break it down in this way? Alpha to the power of k minus 2 into alpha, right? Basically, if you combine this, what do you get? Base same. So you get alpha to the power of k minus 2 plus 1, which is k minus 1. So you can get back here. As long as we can get back there, we can do something like this. If we can go back, this is equivalent, all right? So alpha to the power of k minus 2 plus 1, from there, alpha to the power of k minus 2 into alpha, right? And then alpha to the power of k minus 2 to আছে. এই যে alpha to the power of k minus 1 transforms into alpha to the power of k minus 2 into alpha. Is that clear? Not clear?
Yes, sir,
Confused?
that's
Clear?
Yes, miss.
Okay. All right then. So in that case, now alpha to the power of k minus 1 is being represented in this way. Alpha to the power of k minus 2 into into alpha. And alpha to the power of k minus 2 is already there. So here now you see, now in these two sum terms, there is a common term, alpha to the power of k minus 2. There is a common term here, alpha to the power of k minus 2. We'll take that common term, all right, outside. That is alpha to the power of k minus 2 যদি এখান থেকে common নিই, এখান থেকে যদি alpha to the power of k minus 2 common নিই, what do we get? We get alpha plus 1 left. Alpha plus 1. We'll do the same thing here for beta as well. We have beta to the power of k minus 1 here. K minus 1 is also equal to k minus 2 plus 1. Okay? So we can break it down. K minus 2 plus 1 যদি হয় তাহলে we get beta to the power of k minus 2 multiplied with beta. And here we have beta to the power of k minus 2. Beta to the power of k minus 2 যদি common নেই তাহলে এখান থেকে we get beta and এখান থেকে we get 1. So beta plus 1. Now remember that alpha plus 1 and beta plus 1 are also equivalent to alpha square and beta square respectively. We proved that. We established that. All right? That এই জিনিসটাকে square করলে you will get alpha plus 1. এই জিনিসটাকে square করলে you'll get beta plus 1. All right? So these two are equivalent and these two are equivalent. We've established that. So now এখানে আছে alpha plus 1, beta plus 1. This is the reason we did this. Okay? This is the reason we did this. Sometime in the proof, when you get here, okay, think about, okay, alpha plus 1 কে আমি alpha terms এ কিভাবে represent করতে পারি. Okay, so, and also you should get a hint that alpha square would be your answer because here we have k minus 2. Okay, so ওখান থেকে you should get the hint. Anyway, nonetheless, alpha plus 1 is equivalent to alpha square. We know that beta plus 1 is equivalent to beta square. So here, alpha plus 1 will be replaced with alpha square, beta plus 1 will be replaced with beta square. And once we do that, see, same base, power key, k minus 2 and 2. So k minus 2 plus 2. So you have alpha to the power of k. Base same, power key, k minus 2 and 2. So we have k minus 2 plus 2. So beta to the power of k. So you get the result finally. So we started from the recursive definition, which we know holds true, and then we saw that fk can also be represented using this expression, which is the same as this one. Okay, so we proved basically that pk is true. Since we have proved that pk is true based on the basic step, combining the basic step and inductive step together by the rules of strong induction, we can say that this statement, this expression holds true for all non-negative integers n, all right, to represent any specific number in the Fibonacci sequence. Okay, any questions, guys?
মিস এখানে যে আলফা স্কয়ার ইকুয়ালস টু আলফা প্লাস 1 এটা জাস্ট এই যে আমরা যেটা অ্যাজিউম করে নিলাম ওখান থেকে আসছে, এটা তো ইউনিভার্সাল না, রাইট?
No, ওটা assumption এর সাথে কিছু নাই. Assumption is this part, ঠিক আছে? Alpha square alpha plus 1 তে আমরা মানে alpha কি? What is alpha? Alpha is a constant. Alpha তো একটা constant, তাই না? আমরা তো এই কনস্ট্যান্টটাকে আলফা দিয়ে, এই কনস্ট্যান্টটাকে আলফা দিয়ে রিপ্রেজেন্ট করছি আর এটাকে বেটা দিয়ে রিপ্রেজেন্ট করেছি। তো এইটা, এই কনস্ট্যান্টটারই যদি তুমি স্কোয়ার করো, এটাই তো দেখলাম, তাই না, যে 1 plus square root of 5 by 2, এটাকে হোল স্কোয়ার করলে what do you get in the end? You get 1 plus square root of 5 by 2. See, this term, square of it transformed into this, right? So this is, if this is our alpha, what is this? 1 plus alpha. ওটা তো আমরা কনস্ট্যান্টের জন্য অলরেডি দেখিয়েছি, রাইট?
ইয়েস মিস।
Okay. Yeah, alpha square alpha plus 1, that has nothing to do with the assumption. Alpha, first of all, is a constant itself. So yeah, assumption to na, it's a constant. So any other questions? Okay. So notice some things here. So basic step, how will you know that basic step e kon value jone proof korte hobe, right? So ekhane we proved it for 0 and 1. Will it be 0 and 1 always? No. It won't always be 0 and 1. Basic step e kon value, n er kon value jonno proof korte hobe depends on the recursive definition that you are going to use in the inductive step. See, in the inductive step, we use the recursive definition here where it utilizes the previous two values. Ager duta value ke utilize kore. And it depends also on this base case where f0 is equal to 0, f1 is equal to 1. So from here, you should be able to tell that, okay, এই যে এখানে basic step I have to prove it for 0 and 1, okay? By looking at this, you should be able to tell that. In some problem, this case might be different. So problem to problem, it varies. Base case e tomar basic step e tomar ki proof korte hobe. We'll look at another example. You'll see that it's different there, okay? So similarly, we will use strong induction to prove this identity, okay, for this sequence. We have a sequence here, which is recursively defined. Again, recursive definition here, which is recursively defined with an is equal to an minus 1 plus an minus 2 plus an minus 3. That is, you can get the value in some position based on the summation of the previous two values, given that a1 is equal to 1, a2 is equal to 2, a3 is equal to 3. So these are the base cases of the recursive definition, base case of the recursive definition, and this is the recursive definition itself where I derive the value of some position in the series based on the previous three values, all right? Where in this equation, in this expression, n will never be less than 4, obviously. n less than 4 এর জন্য it's already been defined. n less than 4 মানে কি 1 2 3 ওগুলোর জন্য it's already been defined. And n less than 4 এর জন্য this is not possible. Okay, there is no a0, there is no a minus 1, there is no a minus 2 or something like that. That is index 0 minus 1 minus 2 negative index or 0 basically a specific series doesn't exist. Okay, so we have the indexes starting from 1 and going on until infinity. Now, the recursive definition tells us that given the base cases, that is a1 is equal to 1, a2 is equal to 2, a3 is equal to 3, given that this is the case, any value an can be derived from the previous 3 values. Okay, that is our series sequence. We have to prove that for this sequence, this statement is true. That is an less than 2 to the power of n for all positive integers n. For all positive integers n, an in this sequence will be less than 2 to the power of n. Any number you pick from this sequence, the index of that number, 2 to the power of that index will always be greater than the number. The number will always be lesser than 2 to the power of that index. So an less than 2 to the power of n. We have to prove that for all positive integers. Okay, we'll use strong induction to do that. Okay, in strong induction, in the basic step, again, remember, we prove it for a range of values. So how many values will we prove it for? First of all, before that, what is the lowest possible value of n here?
4.
The lowest possible value of n is 4. What are we trying to prove? We are trying to prove an is less than 2 to the power of n. For what? For all positive integers n.
Miss 1.
The lowest possible value of n is 1. Yeah, 1. N greater than equal to 4 এর সাথে don't get that confused. এখানে what? N greater than equal to 4 এই কথাটা বলা হয়েছে only for this definition. এই definition এর জন্য n has to be greater than or equal to 4. Obviously, n যদি 4 এর কম হয় তাহলে এখানে কি পাবা? If n, let's say এখানে a3 বের করতে চাচ্ছ এই definition থেকে, you have a2, a1 and then what? a0. a0 বলতে আমরা কি কোনো কিছু define করেছি base case? Do we have any a0 in the base case? No. Base case যদি a0 না থাকে তুমি কেমনে define করবে এটা? Also, 4 এর n, for all the values of n less than 4, we have already defined them here. The base case is that a1 is equal to 1, a2 is equal to 2, a3 is equal to 3. A recursive definition এর base case, or a recursion এর base case যেটা. It's already that. So a definition টার জন্য, for this definition, এই equationটা an is equal to an minus 1 plus n minus 2 n minus 3. এই equationটার জন্য n will be always greater than equal to 4. However, আমাদেরকে তো এই equationটা prove করতে বলা হয় নাই. We have to prove that for this sequence defined recursively in this way, a sequence which is defined recursively in this manner, for this sequence we have to prove that an will always be less than 2 to the power of n. Okay, so we have to prove that an is less than 2 to the power of n, and we have to do that for all positive integers n. This is the one we have to prove. So আমাদেরকে যেটা prove করতে হবে, এই proof এর জন্য আমাদের lowest value of n is what? Do you guys not understand my question? See, what do we have to prove? We have to prove that an is less than 2 to the power of n for this sequence. This statement is true for this entire sequence. That is, এই সিকোয়েন্সের যে কোন একটা নাম্বার যদি তুমি নাও, ওই নাম্বারটা যে ইন্ডেক্সে আছে, 2 to the power of that index will always be greater than that number, or that number will always be lesser than 2 to the power of that index. Okay, that is what we have to prove for all positive integers n, starting from 1 and going on until infinity. Okay, that is what we have to prove. So in that case, what is the lowest possible value of n?
Is 1.
Exactly, it's 1. For all positive integers n. What do we have to prove it for? For all positive integers of n. The lowest positive integer is 1. Okay, so 1. But however, unlike induction, we have to prove it for more than that one value. All right, we have to prove it specifically for 1, 2, 3. Why 1, 2, 3? আমরা কিভাবে বুঝবো যে আগের কেসে 0 আর 1, এই কেসে 1, 2, 3? কিভাবে বুঝলাম যে এখানে 1, 2, 3 হবে? Because see, when we are going to prove this, we will use this recursive definition. The sequence itself is defined by this recursive definition, right? আর এই recursive definition যেটা, this utilizes the previous 3 values. And also, this depends on the base case that a1 is equal to 1, a2 is equal to 2, a3 is equal to 3. So by looking at this, you should be able to tell that আমাদেরকে বেস কেসে we have to prove it for 1 2 3 a1 a2 a3 এই তিনটার ভ্যালু যে 1 2 3 এই জিনিসটা আমাকে প্রুফ করতে হবে ওকে by looking at this recursive definition এই recursive definitionটাই তো আমরা নেক্সট ইউজ করব বিকজ মানে এই সিকোয়েন্সটার জন্যই তো প্রুফ করছি সো এই সিকোয়েন্সটা ডিফাইন করা হচ্ছে কিভাবে in using this recursive definition so here the every term is derived based on the previous three values and this definition relies on a1 a2 a3 so in the base case we have to prove that a1 a2 a3 is equal to 1 2 3 respectively and those values will always be lesser than 2 to the power of n for 1 2 3 all of them so we have to prove it for the base case sorry in the basic step we have to prove it for a1 a2 a3 all of them okay so p1 for p1 what do we get here on the left hand side p1 এর জন্য left hand side এ কি পাই a1 what is a1 equal to guys
1
a sequence a what is a1
1
in this sequence a1 is 1 on the right hand side what do we get
2
do we get 1 on the right hand side
no,
2 to the power of 1 remember for p1 n is equal to 1 so here we get a1 which is 1 and the right hand side we get 2 2 to the power of 1 2 so you see
Yeah.
for n is equal to 1 this statement holds what about n is equal to 2 for n is
Yes,
equal to 2 on the
yes,
left hand
yes.
side what do we get a2
2
So
and
it
on the
holds.
other side it is
on the left
4.
hand side we get 8 which is 2 right hand side we get 4 exactly so for 2 as well it holds now for p3 what do we get on the left hand side
3
a3 which is 3 on the right hand side what do we get 2 to the power of 3 which is 8 so the statement holds for p3 as well so see very easily you can see that in the basic step you can prove that this statement is true for 1 2 and 3 and the reason we chose these values 1 is the lowest value and then we went up until 3 to prove that again is because here next you'll see in the inductive step we'll be using the recursive definition আর এই recursive definition যদি ইউজ করতে যাও তাহলে এটার বেস কেসগুলোর জন্য তো you have to prove that this statement holds true and here see every single term can be derived based on the summation of the previous three terms so lowest তিনটা term কে prove করতে হবে ফিবোনাচি এই সিকোয়েন্সের ক্ষেত্রে আমরা যে recursive definitionটা ইউজ করেছি it utilizes the previous two terms so that's why lowest two terms এর জন্য আমরা base case prove করেছি basic step we proved it in the basic step here it utilizes the three previous terms ওর জন্য three lowest values এর জন্য we proved it in the basic step okay because we'll be using this in the inductive step so the inductive step in the inductive step once again we are allowed to assume in the assumption this time because we are using strong induction we can assume that the statement is true for an entire range of values starting from 1 until before k we can assume that the statement is true in the assumption tells us that the statement is true for a range of values starting from 1 until before k based on that assumption what do we have to do we have to prove that the statement is true for the next value what is the next value the next value is k so basically we have to prove that pk is true okay now k minus 3 k minus 2 k minus 1 are they covered in this range এই রেঞ্জের মধ্যে কি k minus 3 k minus 2 k minus 1 পড়ে
yes yes
yes because k minus 3 k minus 2 k minus 1 all of them are less than k and we know from the assumption that all values starting from 1 and less than k for all of those values the statement is true we have to prove that the statement is true for k so k minus 3 k minus 2 k minus 1 all of them are less than k they are within this range so we can say that the statement is true for k minus 3 k minus 2 k minus 1 if that is the case if pk minus 3 is true what does that mean pk minus 3 is true মানে কি n এর জায়গায় k minus 3 হবে এখানে আর এখানে so ak minus 3 is less than what 2 to the power of k minus 3 okay and then pk minus 2 tells us what n এর জায়গায় k minus 2 হবে so ak minus 2 is less than 2 to the power of k minus 2 so pk minus 3 tells us this pk minus 2 tells us this and pk minus 1 is true tells us that this is also true that ak minus 1 is less than 2 to the power of k minus 1 so each of these three statements based on the assumption we can say that these are also true all right based on the assumption that the statement is true for this entire range we can say that these three statements are true okay all right so next we have to prove that the statement is true for k that is we have to prove that pk is true now for pk what is pk Pk is basically ak is less than 2 to the power of k. We have to prove that ak is less than 2 to the power of k. Given that the statement is true for this entire range, we have to prove that ak is less than 2 to the power of k. Okay? Now, based on this recursive definition, ak is equal to what? Guys?
Means a k minus 1 plus k minus 2 plus a k minus 3.
Exactly. We have ak is equal to ak minus 1, ak minus 2, ak minus 3. So see, we are using the recursive definition here. Now, ak minus 1 is less than 2 to the power of k minus 3. ak minus 2 is less than 2 to the power of k minus 2. Sorry, ak minus 1 is less than 2 to the power of k minus 1. ak minus 2 is less than 2 to the power of k minus 2. ak minus 3 is less than 2 to the power of k minus 3. So here, if you sum these up, if you sum ak minus 1, ak minus 2, ak minus 3, এই তিনটা যদি sum up করো, and then on the right hand side, if you sum them up as well, 2 to the power of k minus 1 plus 2 to the power of k minus 2 plus 2 to the power of k minus 3, can we not say that this summation will be greater than the a summation, that is left hand side je summation ta, it will be lesser than the summation on the right hand side, right? If each of these are individually less than these terms, তাহলে আমরা যদি left hand side এর term গুলোকে sum up করি, that summation will be less than the summation of the terms on the right hand side, right? So basically, if we have ak minus 1 plus ak minus 2 plus ak minus 3, each of them individually are less than these individually. So if we sum these up, this summation term will be lesser than this summation term, right?
Yes, miss.
Does that make sense, guys?
Yes, ma'am.
Okay. So in that case, we can say that ak is less than this summation. If ak is equal to this, and this term is less than this, then ak is less than this term, this summation. Yes?
Yes, miss.
All right. Okay. Now, next, what we have to do is from this term, from this establishment so far, that ak is less than 2 to the power of k minus 1 plus 2 to the power of k minus 2 plus 2 to the power of k minus 3. From here, we have to show that ak is also less than 2 to the power of k. Okay. Now, for that, we will try to get a common term from these three sum terms. Okay. How will we do that? First of all, see 2 to the power of k minus 1. Again, if I say that k minus 1 is equal to k minus 3 plus 2, am I wrong?
No, miss.
K minus 1 is equal to k minus 3 plus 2.
No.
That's correct, right? K minus 1 can be represented as k minus 3 plus 2. So 2 to the power of k minus 1 is equivalent to 2 to the power of k minus 3 plus 2. So now if we distribute the base, we get what? 2 to the power of k minus 3 into 2 squared. 2 to the power of k minus 3 plus 2. So alada kore nile 2 to the power of k minus 3 and 2 squared. So 2 to the power of k minus 1 is equivalent to 2 to the power of k minus 3 into 2 squared. Similarly, 2 to the power of k minus 2k, if you break it down, k minus 2, if I say that k minus 2 is equivalent to k minus 3 plus 1, it's the same thing. 2 to the power of k minus 2 is equal to 2 to the power of k minus 3 plus 1. And that can be broken down as 2 to the power of k minus 3 multiplied with 2 to the power of 1. So 2 multiplied with 2 to the power of k minus 3 basically. So 2 to the power of k minus 1 becomes 2 to the power of k minus 3 into 2 squared. 2 to the power of k minus 2 becomes 2 to the power of k minus 3 into 2. And here we have 2 to the power of k minus 3. So now if we take 2 to the power of k minus 3 in common, what do we get? A first term which is equivalent to this, 2 to the power of k minus 3 commonly, what do we get? 2 squared here. A second term which is equivalent to this, 2 to the power of k minus 3 commonly, what do we get? 2 here. And here we have 2 to the power of k minus 3, eta commonly, we are left with 1. So 2 to the power of k minus 3, you take that in common, you have 2 squared plus 2 plus 1, which is equivalent to 7. If ak is less than 2 to the power of k minus 3 multiplied with 7, will ak not also be less than 2 to the power of k minus 3 multiplied with 8? Why? Because this term is less than this. See here, edura comparison dekho. This factor is the same. 2 to the power of k minus 3 to the power of k minus 3, same. What is the different one here? Which one is different? 7 or 8? These two are different. 7 is less than 8. So obviously this product will be less than this product, right? 2 to the power of k minus 3 multiplied with 7 and 2 to the power of k minus 3 multiplied with 8. Difference ta kothay? Difference ta shudhumatro 7 or 8 er moddhe. Which one is the greater term? 8. 7 is the lesser term. So obviously this product will be less, right?
Yes, ma'am.
Confused?
Yes, ma'am. 7 আর 8 কোথা থেকে আসছে বুঝতেছি না।
7 তো আসছে এখান থেকে। এই যে 2 square plus 2 plus 1 কি? মানে 2 square plus 2 plus 1 কেমনে পেয়েছি এটা কি বুঝেছো? Do you understand how we got 2 square plus 2 plus 1?
Yes, from the right hand side. It's explained in the right hand side.
Yeah. So 2 square plus 2 plus 1 we got it from there.
Yeah.
এটা অ্যাড করলে কি হয়? 4 plus 2 plus 1 we get 7, right? What
Yes.
we are saying here is that এখানে যদি 7 পাও তার মানে কি? AK is less than 2 to the power of k minus 3 multiplied with 7, right?
Yes.
Okay. Now, if that is true, we can also say that AK is less than 2 to the power of k minus 3 multiplied with 8, right? যদি AK এটা থেকে if AK is smaller than this, then AK will obviously be smaller than this. চেঞ্জটা কোথায় হয়েছে? Only from 7 to 8. 7 থেকে 8 এ চেঞ্জ করেছি আমরা। If AK is less than this, AK will obviously be lesser than this, right? এটা থেকে অলরেডি ছোট। 7 থেকে যদি আমি 8 এ শিফট করি এটা থেকে তো obviously AK ছোট হবে, because this term itself is less than this. এই দুটো টার্মের মধ্যে C to the power of k minus 3 is the same. The only one that we changed, আমরা চেঞ্জ করেছি কোনটা? আমরা চেঞ্জ করেছি from 7 we changed into 8. 7 থেকে 8 এ চেঞ্জ করেছি। Which one is the greater value? Greater কোনটা? 8 is the greater value. 7 is the lesser value. So this term will obviously be lesser than this term. Does that make sense?
Yes, ma'am.
এই দুটো টার্মে দেখো আমরা চেঞ্জ করেছি, একটা চেঞ্জ করেছি। What change did we make? The only change we made is 7 থেকে 8 এ নিয়েছি। If we went up an integer, তার মানে কি this product will obviously be lesser than this one, right? Because 7 is less than 8. আর বাকি অন্য ফ্যাক্টর যেটা তো সেম রয়ে গেছে। 7 is less than 8, so this term will be less than this one. And we know that AK, so far we know that AK is less than this one. If AK is less than this one and this term is less than this one, AK will obviously be less than this term, right? AK will be lesser than 2 to the power of k minus 3 multiplied with 8. Now does it
Yes,
make
ma'am.
sense?
Yes, ma'am. I got it.
Okay. Okay. So we have that AK is less than 2 to the power of k minus 3 multiplied with 8. What is 8? 8 is 2 to the power of 3. 2 to the power of 3 is equal to 8, right? So 8 multiplied with 2 to the power of k minus 3 is basically 2 to the power of 3 multiplied with 2 to the power of k minus 3. So base same, add up the power, what do you get? 3 plus k minus 3. And what do you get from that? 2 to the power of k. So finally we are here where AK is less than 2 to the power of k. AK is less than 2 to the power of k. এটা proof করেছি মানে কি? We have proved PK. So based on the assumption, we have proved PK. Okay? We've proved that PK is true based on the assumption. So combined with the basic step and the inductive step, we can say that by the rules of strong induction, the statement AN less than 2 to the power of n is true for this sequence for all positive integers n. Okay? We can say that. Any questions regarding the proof? Okay.
No, miss.
So notice some things here. Why are we using strong induction? আমরা strong induction কেন ইউজ করছি? দেখো এই যে রিকার্সিভ ডেফিনিশনের কোনো সিকোয়েন্সের বিষয়ে যদি কোনো কিছু প্রুফ করতে চাই, if you use basically একটা প্রুফে যদি somewhere you want to use the recursive definition, recursive definition টাইপের কিছু ইউজ করতে চাও, তাহলে দেখো at some point see AK is equal to AK minus 1 plus AK minus 2 plus AK minus 3. Okay? So এই ডেফিনিশনটা ইউজ করতে চাইলে আমাদেরকে দেখাতে হবে that the statement is true for k minus 1, k minus 2, k minus 3. Remember, in induction, we are allowed to assume that the statement is true for only one integer, one given integer. একটা integer এর জন্য we can only assume, and from that we have to prove that it's true for the next integer. Here, however, this proof is made easy by strong induction. এই প্রুফটা strong induction এর কারণে easy. কারণ strong induction allows us to assume that the statement is true for a range, not just one integer, just একটা specific integer এর জন্য না, পুরো একটা range এর জন্য we can assume that the statement is true. And using that assumption, we are saying that the statement is k minus 3, k minus 2, k minus 1. Why is it important? Because আমরা যে recursive definitionটা use করছি এখানে ওগুলো লাগবে। Induction কি এটা করতে পারতা? No. In normal induction, your ordinary induction, in the assumption step, in the inductive step, in the assumption, you assume that the statement is true for only one integer, not for an entire range. Okay? And why is it exactly that we went with 1, 2, 3 here, as I've mentioned multiple times? Because as you can see, the equation itself, the recursive equation itself, we get the value from the previous 3 values, and the base case is for these 3 values. So we have to prove that the statement is true for the base cases. Okay, এখানে base case যেগুলো আছে এগুলোর জন্য we have to prove that the statement is true. Same goes with the Fibonacci sequence problem. Base case কি ছিল f0 f1, so ওগুলোর জন্য আমরা prove করেছি that the statement is true. Basic step you have to do it that way. Why? Because this is the foundation of the inductive step. In strong induction, this is the foundation of the inductive step. See, because we have proved it for P1, P2, P3, if what is the lowest value of k? What is the lowest possible value of k in the inductive step? 4, right? For k is equal to 4, the lowest value. What are the previous 3 values? P1, P2, P3. Amra P1, P2, P3 already prove করেছি. Already দেখেছি P1, P2, P3. For those, it's correct. And based on that, we have to prove that P4 is true. And once we do that, for P5 as well, we can use the previous 3 cases, P2, P3, P4, and then we have to prove that P5 is true. And then if you move on to the next one for 6, so far you've already proved it for 3, 4, 5. So you can use those and then you can prove 6. So that is the foundation, okay? All right. So in strong induction, when do we use strong induction? When a certain problem, the solution of the certain problem is made easier using strong induction. Induction or strong induction er modhe legitimacy, if you think about legitimacy, it's not like one is more legitimate, one is less legitimate. It's not like that. Both methods are equally efficient. Whatever you can prove using induction, you can prove using strong induction. Whatever you can prove using strong induction can, in most cases, be proved using induction as well. But it's just that some proofs are made easier using strong induction, and some proofs seem that they'll be easy using induction. For example, any proof that where you use a recursive definition, there, if you use strong induction, it will become a lot easier because the assumption, strong induction or assumption type makes our life easier for such proofs. Okay, that's the reason we use strong induction here. Also, k plus 1 এর বিষয়টা মনে রাখবা। K plus 1 এই যে induction এ here, this k plus 1, proving k plus 1, what does it represent? It represents the fact that we are proving it for the next integer. Not always that you have to prove for k plus 1. It depends on your assumption. Assumption, if you assume it for k, you have to prove it for the next integer, which is k plus 1. If you assume it for k minus 1, you have to prove it for the next integer, which is k. And so on. So tomar proof er jonno whichever is more efficient. For induction, we went with this, okay? Because this made our work look tidier. However, for strong induction, we went with the range in the assumption until k minus 1. Assumption is j range we are assuming the statement to be true. For that, we go on from 0 until k minus 1. And then we prove it for k. Why did we do it this way? Think about it. If you prove it for k, then all you have to do is prove it for 1 by square root of 5 alpha to the power of k, 1 minus 1 by square root of 5 beta to the power of k. Jodi k plus 1 korta, tumi jodi ekhane ei assumption ta change kore bolta, I am going to assume that the statement is true for 0 less than equal to j less than equal to k. You can do that, but in that case, you'd have to prove it for k plus 1. বুঝাতে পেরেছি? তুমি যদি assumption টা change করে এমন বলতা যে the statement is true for all values within this range where 0 is less than equal to j and j is less than equal to k. If you say that, that is the range, at 0 less than equal to j and j less than equal to k. Eta jodi bolo, in that case, you would have to prove it for pk plus 1. Are you allowed to do that? Yes, you are. You can do that. Obhabe proof kora possible. But just to make our proof tidier, that ultimately the end result, it looks a little bit easier or neater if we instead choose the range in the assumption to be until k minus 1. Okay, and then prove the statement for k. In that case, it looks neater. Okay, that's the reason we did it. Okay, that's the end of induction. We're done here. If you have any question, you can ask now. For induction, if you guys find the concept of induction a little bit, if you are a little bit uncomfortable with the concept of induction, what I can recommend you to do is go over the slide and already problem set 1a induction and kishu problems ase, all right? You must have come across induction problem. Remember, I told you right at the start of the semester that you can skip the induction problems until later. This is that later, all right? We are done with induction now. Now you can go back there and solve those problems, the induction problems, try to solve them. Problem set 2, which is from the book. There as well, you have problems from the induction chapter. So you can try them as well. And most importantly, assignment 3, which has already been posted, and if you looked at it, you must have seen that it's pretty much massive, and you have only 1 week to do the entire assignment. There you have many problems on induction. So assignment 3 যেটা তোমাদেরকে করতেই হবে, ওটা করতে গিয়ে you'll practice a lot of things from induction. So try these things out. Every time you struggle, every time you come across a problem that you cannot solve, you can refer to me and clear it out. But for that, first of all, you have to have a very good concept of induction. So go over the slide. First of all, slide-টা দেখো, slide-টা দেখে try to see if you understand induction or not. যদি induction মনে হয় you're still uncomfortable, you're still not clear on how induction works, how strong induction works. In that case, just let me know and schedule a consultation session with me, all right? Okay, any questions?